Welcome back to ECE 442-542. Homework number 3 is due a week from today, and what we talk about today should help you, I hope, get further on homework assignment number 3. Exam number 2, as a reminder, is March 8th, and I put some inverse Z transform notes on D2L that we won't cover in class, but I think will be helpful in homework problem number 2, I believe, problem number 2 of homework number 3. If I have or haven't confused you, hopefully you're clear on what I'm trying to say, but there's some notes to hopefully help you try to inverse Z transform when you have complex poles in the Z-plane. Another problem that is on homework number 3 is dealing with long division, and I want to quickly illustrate how you can use long division to quickly do an inverse Z transform, or how that might make sense. We'll look at region of convergence connections and maybe do a matching. So we'll do some more thumb exercises as far as up, down, or sideways on region of convergence connections. We'll summarize our 3 different patterns for the region of convergence, and then we'll talk about where does this concept of system stability, why is that connected with having our poles inside the unit circle, when it seems like I can have poles outside the unit circle and still have bounded responses. What's going up, or what's going on with that? And then if we have time, then we'll do some observations, making this distinction between signal causality and signal boundedness, and those are 2 separate issues or characteristics. You can have one and not the other, not one and the other. You can have both, but they are independent in terms of this system or waveform characteristics. And if we have time, we'll talk about discrete equivalence, which is how do we take a analog transfer function and put it into a discrete time based transfer function, which we are going to be calling discrete equivalence. You're probably going to get tired of seeing this equation, but hopefully you'll continue to understand it and use it throughout this semester. But it's the definition of the Z transform, and what we want to do now is use this information to try to help us understand how could we apply long division and connect it with this right-hand side, this infinite expansion, to determine the time domain values of our waveform, let's say x of n. That's what we're wanting to accomplish now. And to do that, let's just look at a particular example. Suppose that we start, or somebody gives us a Z transform. Suppose capital X of Z is 4 times Z plus 1 all over Z minus 1/2 and Z minus 2. And if we need to, we might want to just assume that we have a causal time domain waveform, little x of n, that x of n is defined for indices n that are non-negative. But what would happen if we simply did the obvious and performed some division, long division? Now we're going back to earlier grades, but first let's put all of these pieces together. Let's distribute 4z throughout, or we now have 4 times z squared plus 4z in the numerator, and our denominator, if we multiply it out, is z squared minus 2.5z, and I picked these just to be clean maybe. I have 1/2 times 2, and hopefully that gives me 1 with the 2 negative signs. Now, if I do the long division, or if I divide that denominator, z squared minus 2.5z plus 1, into the numerator, 4z squared plus 4z, what happens? Or now I'm looking at z squared minus 2.5z plus 1 and dividing that into 4z squared plus 4z. Or I'm now asking the question, how do I start doing this long division, and how do I make, or what do I need to multiply the denominator by in order to end up with 4z squared as the first term? Hopefully it's clear that I need to multiply that by 4. And if I now do that, I want to take that away from what I started with, which was my initial numerator, but now I have 4z squared. I have 2.5 or 4 2.5s with a negative sign. I think that's now 10. 4 quarters is $1. That helps me get to 10. And now I have 4 and 1, or 4. Which, if I subtract those, or that line, the black line from the blue numerator that I started with, I end up with no more z squared terms, good. And I now subtract a minus 10z from 4, or I'm now adding 10 to 4, I end up with 14z minus 4. And now I want to find, what do I need to multiply by z squared to end up with 14z? And I can have negative exponents. Or hopefully now you can see that I now need 14z to the minus 1. Or now if I push that 14z to the minus 1 through my original denominator, I end up with 14z. I have 2.5 14s, 28 plus 7. Is that true? So I now have 35 with the negative sign. I have minus 35, z to the minus 1. Those cancel, so I end up with just minus 35. And I have plus 14z to the minus 1. Is it clear where these terms are coming from? I'm simply doing long division, except now I'm using polynomials, and I may need to start multiplying or having in my numerator negative powers of z. Question? So where did the negative power of z come from? Now I'm trying to find a quantity in that second term in the numerator that when multiplied by the denominator, z squared, I end up with 14z. I now want to take something times z squared and end up with 14z. I can get the coefficient by multiplying by 14, and now I need to lower the polynomial by a factor of 1, so there's my z to the minus 1. Z to the minus 1 times z squared gives me the z that I'm looking for. Does that help? Question was, where did that 14z to the minus 1 come from? And again, we can do our subtraction. I'm now adding 35 to 4, or I now have 31, and I subtract the 14z to the minus 1. And what's my next term that I need in the numerator? And do you see that we could just go on all night doing that? We're going to just keep going and going and going, but my Energizer might run out. So I'm going to stop. I'm just going to put some dots. But what I want us to see is connecting this expression, the result of taking our numerator and dividing it by our denominator, and comparing that with that expression. And I'm trying to match terms. And if I match terms, you can see that I don't have any positive powers of z. meaning all of my negative indexed little x's are not present in my expression for x of n, but all of those coefficients down here in the lower circled highlighted in yellow correspond to the x's at certain time indices. Meaning, if I looked at this particular term, do you see that that's now scaled by z to the 0? And I come up here and I say, what's scaling z to the 0? Well, that's now my value of the time domain waveform x at time index little n equal to 0. Likewise, 14 ends up being little x at what time? That's now little x at time 1. And now do you see that I'm finding my waveform, my x of n, at different values of little n just by doing long division. And this 31 is now the time value of x at time 2, n equal 2. And I could just keep going. This may not be a very efficient way to find the inverse z transform if you're trying to find all of the equations or the coefficients or the time domain. But if you're just wanting the first two, maybe this is quicker than doing the inverse z transform and finding a closed form expression. So if somebody wants to know what's x of 0, what's x of 1, and that's all they want, well, that was not too hard to find. We didn't have to look up any tables. We didn't have to do a lot of mental exercises, and it came to us fairly cleanly. But this is what you're going to be asked to do on one of your homework problems. Long division, okay? But it's just with polynomials. So if I start asking about long division, this is what I'm wanting you to try to produce. Questions on that? Another way of finding the inverse z transform. Now, I've spent a lot of time creating this graphic, so I want you to be very appreciative. Sort of looks like an eyeball, but let's get beyond that. Well, maybe if you want to just, if it's looking at you, that's okay. But I'm trying to now provide 3 different region of convergences. I have a green region of convergence, which is inside all of my poles. I have poles at 1/2, 3/2, and 2. So one possibility of a region of convergence is the green, the inner disk. Another region of convergence, which I'm calling region of convergence number 2, is the blue annular region that's shaded in blue. And that now is bounded on the inside by a pole at 1/2 and on the outside by a pole at 3/2. But I have an additional pole beyond that. But I do have an annular region of convergence, and that's blue. That's region of convergence number 2. I have a third region of convergence, which is, I didn't want to spend my entire day coloring, but you can imagine that's now this unbounded region that's black, or I've shaded it gray, and that goes on forever. It's unbounded, and that one lies outside all 3 poles. A pole at 1/2, 3/2, and 2. And now what I want you to do is play this matching game and match 1, 2, and 3, regions 1, 2, and 3 with, I don't know what color that is, but I wanted to change color. A, B, and C, A being causal, that's thumbs up. B being two-sided, I wanted to go naturally, A, B, C, and I don't care if you go clockwise or counterclockwise. If one is easier than the other, just do the easy one. And C is anti-causal, that's thumbs down. But ideally, if this was on the exam, maybe I would just have you connecting these with lines. If I wanted you to match, maybe you would just say, oh, there's one, there's another, etc. But I don't want to give you any suggestions as far as what might be the match. But Does everybody have answers in mind? For number 1, region of convergence number 1, maybe I should have been consistent since that was green. For region of convergence 1, what do I match with 1? A, B, or C at the count of 3? Is that clear? Let me put my eye on, although there is already an extra eye staring at you. And it's green with a blue iris. Never mind. So, A, B, or C on the count of 3. 1, 2, 3. So I see most thumbs are down, so that would be C. Correct. So that's anti-causal. Hopefully no one broke a thumb trying to answer that question. Number 2. Whoops. Region number 2 is A, B, or C on the count of 3. Is it causal, two-sided, or anti-causal? That's number 2. 1, 2, 3. Okay, so now we have quite a few horizontal thumbs, which is good. So that is what? B. And 3, whoops, which is my third color, A, B, or C. Right on cue. Check the time. Did you hear the audio? There was an I'm sorry. Do you know what it was? Yes, someone stapling posters. And it was my grandmother, actually. And she said, I'm sorry. Now you want to see what my... Never mind. Number 3. Region of convergence. Now we know when that happens, right? On evenings at somewhere between 5:30 and 6, somebody starts posting all of those posters outside our door. Maybe she'll be quieter next time. We'll see. A, B, or C? 1, 2, 3. We end on a positive, right? Thumbs are up. This is A. All right, good. Now, one more matching opportunity. This is now, how does the signal behave? Are the signals bounded and they decay exponentially? That's A. Are they bounded with no decay? Is that clear what I'm meaning by B? No decay. It's either constant or maybe it's oscillating, but it's bounded. It's not growing. It's not going to 0. It's not exponentially decaying, but it's bounded. That's answer B. Answer C is an exponential growth. Okay? And those I want you to associate with these same 3 pole locations and these regions of convergence. In this case, let's start with the green. Region of convergence number 1. And at the count of 3, A, B, or C. Okay? Are we ready? So region of convergence number 1 together with those 3 poles. Does that give us bounded, decay exponential, bounded, or unbounded, which is C, and that's the downward thumb? Up, parallel, or horizontal, or down? 1, 2, 3. Now I have quite a bit of variation. So what are we seeing relative to this first question? What are the modes that we would see in our answer? Or when you got the first part right, the first matching quiz, so when is this region of convergence, what does it correspond to in terms of when is this signal defined for what values of n? For what values of n is region of convergence number 1 defined? Really? You're going to force me to scroll? C. Well, it's anti-causal. Now the A, B, and C are different, right? So now we have n less than 0. But if we now call this x of n, one of the modes is due to 1/2, is it not? And we're now raising that mode, so let's call this x partial. That's one of the modes. We have another mode at 3/2 and another mode at 2, and we're raising all of those to n. Now, if I raise 1/2 to a negative power, what am I going to see? I now have 1/2 raised to a negative power. I could think of that as 2 raised to higher and higher powers. 2 squared, 2 cubed. What's that doing? Is that growing? Is it growing unbounded? So which answer was number 1 supposed to be? C. So that should have been a thumbs down. Right? So if you got that right, you can give yourself. All right, number 2. Region of convergence number 2 is this annular region, and I want to know, is it bounded, decaying exponential for A, up, horizontal, or unbounded for down? So region of convergence number 2, on the count of 3, I want to see thumbs. We ready to answer? One. You guys aren't telling me you're not ready. 2, 3. Why is it bounded? What modes do we have present? Let's say this is now x of n. We have an alpha 1/2. Well, when is 2 defined? We have this plus beta 3/2 to the n plus gamma 2 to the n. But when is n defined? Everywhere. It's two-sided, isn't it? And when are these valid? When is the 1/2, the 3/2, and the 2, are they always on? Where is 1/2 relative to the region of convergence? Or where is the region of convergence relative to the 1/2? It's the region of convergence there is outside, and when we are outside, our region of convergence is outside our poles. When is that set of poles defined? Yes? So what's that mode doing as we increase n? Is it okay? 1/2, 1/4, etc. What about the other two modes? Where are they, or where's the region of convergence relative to the other two modes? They're left-sided, aren't they? So these two are defined for n less than 0. So now we have 1/2 downstairs raised to higher and higher powers. That seems to be shrinking. And 2 downstairs raised to higher and higher powers. That's also shrinking. Which means, what's this doing relative to behavior? As a function of n, let's just say we're doing this for n positive or non-negative, and what's happening for negative n's? You said it was shrinking as well. Now, what's the answer? A, B, or C? From this picture, if I gave you that picture on the final or on an exam and I said, is this response, is this waveform bounded, decaying exponential, unbounded, growing exponentially, or bounded, what would it be doing? Do you see that it's well behaved? It's exponentially decaying, both negatives and positives. What about number C, or number 3? Yes, question? Scroll up. Yes, the region of convergence is the blue donut, only the donut. So the region of convergence now, the question was, why do I have the 2 in there? Now I just have bounds. I have to be bounded by poles, my region of convergence. But some poles could be inside or outside that region of convergence, since it is annular. I could have another pole, a fourth pole at 1/4, and that's okay. I could have another pole at 1/8. I could have 10 different poles, but right now I'm saying I'm concentrating on my region of convergence being bounded between 1/2 and 3/2. Is that clear? So I could have some more poles even somewhere else, maybe at -3, and this same behavior would be exhibited. Pardon? What if I had a pole at 1? What's the answer there? Not with that region of convergence, right? What did I say about poles and regions of convergence? Poles can't be in the region of convergence. So I couldn't have a pole at 1 and have that region of convergence. You would have to say, hey, Tharp, is there a typo? What's going on? And then I would say, would you just whisper that? You're maybe giving the answer away on the exam. But you would then write down maybe on your answer, this is inconsistent, this problem. I can't have a pole inside my region of convergence. Is that clear? Thumbs up? Good. Now, the third case, region of convergence number 3. And I'm going to have to give myself a little bit more space. Number 3, A, B, or C? We ready to vote? A is bounded exponential decay, B is bounded no decay, that's horizontal, and C is down, that's unbounded exponential growth. So region of convergence number 3, 1, 2, 3. I have some confused thumbs, sort of. Where are all of my, well, where's my x of n defined? For what values of n? You got this one right in the first part, right? It was A. It was for non-negative n's. And what modes do we now have? We have the same modes that we had in problem 2, except now they're all defined for n greater than or equal to 0. Correct? So now I could say, oh, I have x of n equaling alpha to the 1/2 to the n plus beta 3/2 to the n plus gamma 2 to the n, and all of those are for n greater than or equal to 0. Now, do you see a problem with the behavior here in terms of how it might behave as a function of time? That 2 or that 3/2, that's a number that's bigger than 1, which you're raising to higher and higher powers. Now do you see that this is going to be growing exponentially and be unbounded? That likewise is C. So I didn't have a B. It was either A or C on that problem. Questions on that matching example? Yes. So when would I have bounded with no decay? When would I have bounded with no decay? Let's, whoa, where'd my eye go? What would give me a bounded response? Any of these poles give me a bounded response. Do any of these right now that I have on the board that don't decay or grow? No. Where do I have to be for a response for a pole to give me a bounded behavior? No hints whatsoever. Isn't that the unit circle? So, what? I probably don't want to know what was just said, so we'll move on. Unit circle. Never mind. Luckily, that doesn't come through on the video. But you need to be, your poles have to be on the unit circle to be bounded. And then they would be sinusoidal. If it was at z equal to 1, then it would just be a constant. So if we had poles on the unit circle, we could have that defined for, if we had a region of convergence inside of those, it would be anti-causal, but it would still be bounded and without any exponential behavior. Or we could have poles, a region of convergence outside of the unit circle and have poles on the unit circle, and that could give rise to a bounded behavior. Does that answer your question? So if you're looking for sort of answer B, then we would have to have poles on the unit circle. And our region of convergence would have to be consistent with those poles. Meaning we couldn't have this blue region of convergence, could we? Because we can't have poles in our region of convergence. Other questions? Yes. So now the question was, do all of the poles or just some of them have to be on the unit circle? So let me, well, we may get to this in a minute, but let me give myself some more space. That's the problem with trying to anticipate. I should have made it so confusing no one had any questions, right? No, that's not the goal. But I just said bounded. Let's say no decay corresponded to, and those have to be in conjugate pairs, or there's one on the unit circle. The second question, I believe, so let me say question 2 and give myself some more space. What if I had the following? Let's say that's at 1, and let's say this is at j and minus j. I could be anywhere on the unit circle, so you assume that that's on the unit circle. Let's say that is the unit circle. Oh boy. That's okay. It's on the unit circle. Oh, that's painful to look at, but you don't have to concentrate on the unit circle. But let's say that I now had some other poles. And my region of convergence is outside here. When is this x of n defined? For what values of n? For this region of convergence. I better label this, because if you go back and you say, I have no idea what that red thing is, it's supposed to be the unit circle. When is this picture corresponding to little x of n, when is that true? Or when is it defined? For what values of n? This is causal, is it not? These are causal. And now, is this going to give rise to a bounded response or exponentially decaying response? What's it going to do? We're going to have many modes, yes? We have modes due to every pole, and the modes that are complex conjugate are going to be sinusoidal, but the ones inside the unit circle have a decay, correct? They're exponentially decaying sinusoids, sinusoids being cosines and sines. So all of those poles inside the unit circle are decaying. The ones on the unit circle, what do? They just sit there and shake, right? There's no decay, because what's their magnitude? What's R? R is 1. We hit 1 with higher and higher powers of n. What's it doing? It's not decreasing, it's not growing. It just sits there and shakes. So this has some modes that decay, but you would have to say that if you excited this system, if you kicked it, it's going to just oscillate. This one pole at 1 will give you a constant behavior, and the others that are somewhere else on the unit circle, they're going to be shaking with a sinusoidal behavior. Depending on what? Depending on their angle relative to the real axis. That governs their sort of frequency of oscillation. Does that answer your question? So now I forgot the question, but I answered it apparently. Oh man. I have it recorded. I could play it back. I may get stuck, and it may just, I may have to watch the unit circle video. Questions? Any other questions? But I think this one was, what if you have more poles? Or can you have more than one pole on the unit circle? No? Oh, do all the poles have to be on the unit circle? Thank you. Is that okay? So what is this classified as? Is this classified as you're wanting an A, B, or a C? No D's or E's? Which one is it? A, B, or C? The response due to that system. You're going to have two pieces, really, but what's going to dominate the behavior? The one that just shakes, the bounded one. The others are going to exponentially decay. So this one would be B. I would say it's B. You have a bounded response, because there's some that just keep going and going. And I'm not here to keep going and going. Obviously, I can't even remember the questions. Questions? Reminders? Let's scroll through those unit circles quickly. Summary. We have three different patterns, three possible patterns. Pattern 1 is an unbounded region of convergence. That's beyond all of the poles. All of the poles are interior to this region of convergence. That gives us a causal. or non-negative indices where it's valid. Will it be bounded, the time domain waveform? Trick question, right? It depends on what A is. If A is outside the unit circle, it's unbounded. If A is interior to the unit circle, it's bounded. But you know causality from this pattern of region of convergence. So if you just see this region of convergence, nothing else, no label on A, you can conclude it's causal. You can't say anything about the bounded behavior of this waveform until somebody labels A. Pattern 2. This is now the disk. Now all the poles are exterior to. So I could have more than one pole, but they all have to be beyond this region of convergence, and the smallest pole will bound that region of convergence. This is now anti-causal, or for negative values of n. Pardon? Why is it non-causal? So I'm just calling it anti-causal or non-causal. So I'm trying to distinguish between causal, n greater than or equal to 0, and anti-causal or non-causal being n less than 0. That's the way I'm defining my causals. Is that okay? Pattern 3. Oh, and what do you know about the bounded behavior of this waveform? It depends again, right? Depends on where A is. If we want this to be bounded, where do you want A to be? You want it to be outside the unit circle, don't you? You want it to have a magnitude bigger than 1 to be bounded. Pattern 3. I don't want to scroll. Well, I will. Wow. Now, can you shrink your paper in real time? I'm mean, aren't I? Yeah, you can, yeah, and then you can staple it on the bulletin board. You can wad it up. All right, so this is pattern number 3. It's two-sided. B now is exterior to that, so that's the anti-causal, or the time when n is less than 0. So there n is negative. The other piece, the A pole, is interior to the unit, or to the region of convergence, and so that's defined for n non-negative. And depending on where A and B are located will determine whether you have a bounded or unbounded response waveform. And this other curve, I don't even know if you can understand it. In the right hand, somebody obviously has asked me in the past, that's not a region of convergence. Why? You see that little dashed line that an ant was trying to move? It can't go from A to B without leaving the region of convergence. So that's not allowed. The region of convergence needs to be connected. We okay? Question. So now the only way that it can be causal and stable is if we have poles inside the unit circle. All of our poles. We'd have many, many poles, but they would all have to be inside the unit circle. Because then the biggest one, the biggest R of those, would be the bound on our region of convergence. And as long as its R is less than 1, then our region of convergence is beyond that, and it also contains the unit circle. And that would be the dominant pole. Typically, you want that pole to be closer to z equal to 1. If it was close to -1, it's flip-flopping back and forth. It's erratic, but yeah, it might sort of, I prefer to sort of think of the poles near z equal to 1 dominating the response. And I think you basically just answered what or asked a question about what I wanted to talk about now, which is really not so much waveform behavior, bounded or unbounded, but now let's talk about system stability. And that's really what we're dealing with, since this is a controls class. And what we want to know or think about are having poles inside the unit circle for stability. So where does that concept come from, or why? Why do you get bombarded with, I need my poles of my system inside the unit circle in order to be stable? Let's just think of this in a picture setting. Suppose this is the system, and we're exciting that system with some waveform, some signal, and we now are getting some response, the output. So this could be, let's say, an R, and if we were in the time domain, that might be R of t, but if this is the digital controls class, we might say that's R of n, and this is Y of n. Now, our physical systems are what? You kick them and they respond, right? It's not they respond and then you kick them. They're not anti-causal. The systems that we're dealing with in this controls class are causal, meaning they respond, or the response occurs after they are excited. Since the response occurs after excitation, or this now says for n greater than or equal to 0, do you now see what we can draw relative to the z-plane and stability and region of convergence relative to the unit circle? If it's causal, let's say that's the unit circle, you're going to get confused on what a unit circle is, but you can go home and get your your compass. You could do a protractor, I guess, and trace around it, but now your compass, you can get any size circle you want, but you can now make it a unit circle. Now what we're saying is that we want all of our poles, wherever they might be, to be inside this unbounded region of convergence that's indicated in red, and that region of convergence is including the unit circle. Is that clear? So because we're dealing with systems, that's where typically when we're looking at a system, we want all the poles to be inside the unit circle because our system is causal. We're only studying this for n greater than or equal to 0. It's only when we start to look at this broad picture of z transforms and waveforms where we start talking about negative n's, n's positive, etc., that it gets a little bit more interesting as far as bounded and unbounded waveforms. Meaning, we have this observation that can be made, and that is this sort of disconnect or independence of signal causality and bounded time response. And those two are actually two separate characteristics. By that, I mean the following. A signal can be causal, where causal, I'm saying, is defined for n greater than or equal to 0. And where's the region of convergence relative to the poles? In a signal that's causal, where's my region of convergence? Pattern 1, pattern 2, or pattern 3? Maybe I don't want to remember or memorize 1, 2, and 3, but the region of convergence is blank to all poles. Interior, exterior, or annular. So the region of convergence is outside all of my poles if it's causal, right? So this is region of convergence is exterior to all poles. So a signal can be causal, yet unbounded. What's going to give me an unbounded response relative to poles or their location? I just need one to be in this location to cause my whole waveform to be unbounded. I could have more than one, but it just takes one. And as long as that one pole has a magnitude beyond the unit circle, then the response is going to be unbounded. Example, suppose I said h sub 1 of n is 5 to the n, and that's for a causal waveform for n greater than or equal to 0. Picture-wise, I now have a pole at 5, and my region of convergence is exterior to that. My region of convergence is unbounded. My waveform is unbounded. But those are not necessarily having to be the same. What about the other case? Or another case, let's call this the flip side. A signal can be non-causal That's what we're defining for negative values of n. And where is the region of convergence in this case? This one's interior. This one's now the disk. So now my region of convergence is interior to the poles. I could have a signal that's non-causal, yet unbounded as well. Where do I need a pole to give rise to an unbounded response when I have an anti-causal or a non-causal waveform? And again, it only takes one pole. Now we need one of those poles to be inside the unit circle to give rise to an unbounded behavior. One such waveform could be 3/4 raised to the n for n less than 0. And that mode is given by a pole at 3/4. And the region of convergence is interior to that pole. In this case, I have a bounded region of convergence and an unbounded time domain response. My response in this case, not sure why I made it so far to the right, but now I have at -1, I have 3/4. Well, let's say that I had a weighting or a scaling of 1, so this would now be 4/3. I now would be squaring that, 16/9, or 16/9. Then I have (64/27), etc. And that just keeps going. We could just keep going with this, couldn't we? There's 2 more cases that we could talk about. We could have a causal sequence that is bounded. Let's say that's now h3 of n. What's a possibility there? If it's causal, when do we know it's defined? N is greater than or equal to 0, and we could pick any mode. Give me a mode. It needs to be where? Less than 1. So let's just say this could be 1/4 to the n. That's a bounded waveform. Where's the region of convergence? If it's causal, we know it's outside. It's unbounded. We have an unbounded region of convergence, but a bounded waveform. And finally, let's say number 2 is a non-causal sequence that is bounded. Will that do the trick? All I needed was what for R? R being that number 6 in this case, I just needed that to be outside the unit circle. So that now, if I looked at this, and if that's my pole, where's my region of convergence? Is it annular? It's supposed to be corresponding or consistent with non-causal. What's the pattern for non-causal? Now it's bounded, isn't it? My region of convergence is bounded. And now I have 6 raised to higher and higher, more and more negative powers. -1, -2, etc. So now I have 1/6, 1/32, 1/36, etc. You should all be experts now on region of convergence and bounded behavior of waveforms and how to come up with examples. And that's important for the following reason. If we want to now, if somebody gives us a transform, a z transform, can we tell them what little x of n is? To find a unique inverse or a unique x of n, we actually need two things. We need the capital X we need capital X of z, and what else do we need? We need the rock, don't we? We need the region of convergence. Everybody's looking for a rock. I don't have any rocks, except up here, right? Example. Suppose x of z is now z over z minus 1/4, z minus 2, and let's say that somebody also tells us, since we need it to get little x of n, we need a region of convergence. Suppose that they say that the magnitude of z is bounded on the small side by 1/4 and on the big side by 2. And I am expecting now, based on what you know, to start asking questions. And it may not be in this order, but let's just pretend. What's one of the questions? That's rhetorical. I'm going to answer it. Where are the poles located? That might be a question, right? That you're thinking. You're trying to get a mental image of what is little x of n. You might say, where are poles of x of z located? And if that question was asked, could you answer it? Or could you provide the poles? You better be able to, because I've already factored the denominator. We have a pole at 1/4 and a pole at 2. We only have 2. We have a second order denominator. Then we might ask another question. Question 2. Is little x of n one-sided or two-sided? If you're hungry, are you going to be fed by this region of convergence? Or are you going to be disappointed? Both? Okay, you have very high standards on eating. I get that. But if this was a donut, or maybe she sampled the region of convergence and it gave her the hiccups, right? So now what's our region of convergence? It's annular. It's a donut shape. How do we know that? Just by looking at the definition. It's bounded on both sides. It does not include the origin, and it does not include infinity. It's bounded by two poles, one at 1/4 and one at 2. Another question. What's the structure of X of n? Or is it maybe clear what I'm asking? What are the modes? Do I have more than one mode? I have modes that result from my poles. These are real, so these modes are pretty easy. I have one mode at 1/4, so that will be 1/4 to the n. And I have another mode at 2. But now can we say anything more about that exponent n in one or both cases? Where is the region of convergence relative to that pole at 1/4? Can you see the picture without me drawing? My drawing might confuse you anyway. Where's the region of convergence for the pole at 1/4? Interior or exterior to the pole? So the region of convergence is exterior to the pole, and what does that mean? So now we have a right-sided or n greater than or equal to 0. What about this mode? Where is the region of convergence relative to that pole? And what does that imply? This one now is defined for n less than 0. We don't know the scaling, the coefficients that weight these modes, but we know these modes. We have a mode at 1/4 and we have a mode at 2. Now that we know that and when those n's are defined, can we ask another question? Is X of n a bounded sequence? And you can answer this many different ways, but you better be consistent with your answer. What's one way that you could answer this question? One way? And now I've got thumbs pointing everywhere to the neighbor, huh? Which neighbor do I want to ask? Who wants to volunteer? Can you tell me the answer based on the answer to 3? Yes, because now you know the size of those modes and how they are behaving relative to the n's, the powers that they're being raised to. I have something less than 1 being raised to higher and higher positive powers. That's bounded. I have something bigger than 1 raised to negative and more negative powers. That's bounded. What's another way of answering question 4? What do we know about the region of convergence and the unit circle? Where is the region of convergence? It's between 1/4 and 2. What lies between 1/4 and 2? 1, our unit circle. The bounded behavior of our sequence now is also could be explained since the region of convergence contains the unit circle. Now, what if we want to actually find the actual X of n? Now we have all of this information. We know it's well behaved. We know what the modes are, but we want to know the weightings on those and how to define little X of n. But now it what? Has two different pieces. It has one piece that's defined for n non-negative and another piece that's defined for n negative, for the n's as the argument. So we actually need to split this capital X of z into two pieces to give us the two-sided X of n. We know the 1/4 mode holds for non-negative n, and we know that the 2 mode holds for negative n. How do we find the answers that we want? The weightings on the 1/4 and the 2. And if you're playing along at home and you're watching the clock, you know I'm giving you all the answers at this point, right? We can do a partial fraction expansion. Of course, at home, you're probably listening to this at quadruple speed. If you're in class, you don't have that option, but you probably checked out. No, everybody's paying attention, right? All right. What's x of z over z? That's 1 over z minus 1/4, z minus 2, or that's now a, z minus 1/4 plus b, z minus 2. And we can find the a and the b. Yes? So a, let me just give those to you, is minus 4 over 7, and b is 4 over 7. So that now x of z is minus 4 over 7 z over z minus 1/4 plus 4 over 7 z, z minus 2. And I'm going to now call this one x1 of z, that's my splitting, and here's x sub 2 of z. If that's the case, what do I know x sub 1 of n is? That's directly from one of the pairs in my z transform table. It's something z over z minus 1/4. And that something is minus 4 over 7. The 1/4 gives me my common ratio, and that's true for n greater than or equal to 0. X sub 2 of n is now 4/7, 2 to the n, for n less than 0. Now, suppose somebody wanted to write that as one equation without the curly brackets and dividing it into 2. What I want you to be able to see is that we could also write this as 4/7, 1/4 to the n times u of n. This gets back to an earlier question. U of n now is a switch, and it's only turning that expression on for what values of n? Non-negative values. When n is 0, that kicks on, does it not? And then we have this other piece, which is 4 over 7, 2 to the n, u of minus n minus 1. Where in the world did that come from? Well, pay attention to when the argument of that unit step is non-negative. In this case, we want that to be turning on. We want that switch to be activated for negative values of n. What happens at n equal to 0 in that second term? U of minus 1. Is it on? No. We want that argument to be 0 or positive. What about minus 1? Now we plug in u of minus a minus 1 plus 1 minus 1. u of 0. So now it kicks on at minus 1. What about any more negative values? U of minus 2, it's on. U of minus 3, it's on. What about the u of n? Is it on? The first term is not on if n is negative. So what I am suggesting that you do is look when this argument, so here, you would say my argument minus n minus 1 is equal to 0 when for n equal to minus 1. And when is this guy going to be turned on? This will be turned on for n, or at n equals 0 and all values of n bigger than that. Is that clear? So watch when the argument is non-negative. And that then allows you to write this expression as one equation without having to do the curly brackets. We'll pick up with discrete equivalence the next time we meet.